welcome to today's webinar, announcing Amazon EC2 F1 instances with custom FPGAs. Our presenter today is David Pellerin. David is a business development principal for high-performance computing at AWS, with a focus on high-scale applications in engineering, manufacturing, financial services, life sciences, media, and energy. Prior to joining AWS, Mr. Pellerin had a career in electronic design automation and hardware-accelerated computing. His experience with circuit simulation and synthesis, grid and cluster computing, and embedded systems. Mr. Pellerin is the author of 5 technical books, including Practical FPGA Programming in C. Today with us, we also have Chris Petty, Gadi Hoot, and Nafa Bishara. They will serve as our webinar moderators and will engage with you and answer your questions throughout the presentation while David presents. David, welcome. The floor is now yours.
Well, thank you, and thank you everyone for joining today. We're very excited about the new F1 FPGA-based instances, and I'd like to walk you through some use cases, talk about the design flow using the F1 instances, and talk about why hardware acceleration is so important today. I'll start by talking about the basic concepts of accelerated computing, why this has become so much more important, how parallelism fits in creating much more efficient accelerated applications. I'll then dive deep into the F1 instances themselves, what the architecture looks like, the types of FPGAs that are in there, the interconnects that are provided. We'll then talk about use cases. I'll highlight a few specific examples of partners that are quickly deploying on the F1 instance, taking advantage of FPGAs in a variety of different sectors. And then we'll go a bit deeper into the FPGA development process. How do you get started? How do you create logic that's programmed into an FPGA in the F1 instance? And perhaps equally importantly, how do you then deploy that to customers or for your own applications in a secure manner? So let's start by talking about accelerated computing in general, the concepts behind this, how parallelism fits in and pipelining. The first thing to understand is that accelerated computing is not new. In fact, if you look at processor architectures and hardware acceleration architectures, they've actually been around for quite some time, all the way back to the days of the 8086 and the 8087 coprocessor and other similar hardware accelerated capabilities that have been used in conjunction with CPUs. In the AWS cloud, accelerated computing has been around for a while also. In fact, if you go back to 2010 when we first released the CG1 instances, those are absolutely intended for accelerated computing using GPUs. And we've continued to innovate over time. The G2 instances, GPU-based accelerating graphics, the recently announced P2 instances that are compute acceleration platform based on NVIDIA K80 GPUs, and then of course now with the FPGA-based F1 instance that we'll be talking about today. So we continue to innovate, we continue to add new instance types and new capabilities in response to customer needs. So GPUs and FPGAs, why these for accelerated computing? They're really very different, but they serve a similar role, and that is to create massive levels of parallelism to create specialized accelerators for particular applications. If we characterize GPUs and FPGAs as accelerators, they are absolutely flexible in terms of what you can place into them, but they're less general purpose than, for example, a CPU-based architecture. And we'll get into the details of that in just a few moments. The differences between GPUs and FPGAs can be summarized as a GPU is an instruction set machine. It has computation cores. In the case of NVIDIA, these are called CUDA cores. And these are instruction-based, and they allow you to create very parallel applications using familiar programming methods. CUDA, OpenACC, OpenCL. GPU acceleration is supported by a wide variety of software packages and ISVs. There's a lot of good quality software out there that is accelerated today with GPUs very effectively. FPGAs are quite different. They also provide vast levels of parallelism, but in a different way. FPGAs are not instruction-based. They allow you to create custom instructions, custom data paths, custom operations to meet the needs of specific applications. They're very flexible in allowing you to create deeply pipelined algorithms, for example, or to use alternative bit widths, alternative data paths. Another way to think about accelerated computing is with the idea of transportation, right? So think of a business jet, think of a high-performance aircraft. This is similar to a CPU in that it has a limited number of seats. It can't really be reconfigured to be different sizes, but it's very flexible, very general purpose because you can fly it anywhere and land it anywhere, and it moves very, very fast, right? It's all about getting the passengers from point A to point B at a very high speed, and point A and point B can be very different depending on the needs of the application. If you think of a multi-core CPU today, maybe that's a fleet of jets, right? An FPGA or a GPU, on the other hand, is all about throughput. It's all about creating massive levels of parallelism, perhaps moving more slowly from a clock speed perspective than that jet, but the ability to add more and more seats to it, to add and subtract cars. Throughput is what this is all about, and efficiency. Diving a little bit deeper into the different architectures, right? So a CPU, because it's general purpose, a lot of what happens in a CPU is about abstracting the underlying hardware, making it possible to use high-level programming languages, to have operating systems, to allow lots and lots of different applications to run in that CPU simultaneously. So many of the transistors, in fact, most of the transistors in a CPU core are doing control functions. They're doing cache operations. They're there to move the data in and out of a relatively limited number and a fixed number of arithmetic logic units, ALUs. GPUs take this the next step by adding far more parallelism, many, many more compute engines or cores, if you will, GPU cores. In the P2 instance, for example, which is based on the NVIDIA K80, each of the 16 GPUs that are available in the largest P2 has 2,880 of these CUDA cores. So you can have vastly more parallelism, but they're somewhat more limited in terms of the ability to support a wide variety of applications, operating systems, multi-threading and so forth in that GPU. They're very, very good for acceleration of certain classes of applications, not just graphics. FPGAs take that parallelism to the next degree. So now we don't have an instruction set. We don't have fixed data paths, fixed data widths. We really have the flexibility to build whatever hardware we need in that FPGA. It's a much more granular type of architecture. In the case of the F1 FPGA, the VU9P that's used, the Xilinx VU9P, each of the FPGAs in F1, we provide greater than 2 million of these logic cells that are available for custom programming by developers. Another very important point that I touched on a moment ago is the ability to create different sized instructions, different sizes of data paths. This is a very important distinction between CPUs, GPUs, and FPGAs. The ability to create data paths and instructions of 2 bits, 4 bits, 10 bits, whatever width you need to create efficient pipelines and operations for your applications. When you think about FPGA-based acceleration, the FPGA is being used in combination with a host CPU. The idea here is that the bulk of the application continues to run in the CPU. It's doing data management, control plane sorts of things, a wide variety of different applications or threads can be running in the CPU, while the heavy lifting of computation is happening in the FPGA. And there's different applications that have different I/O characteristics. We'll talk about some of those a bit later. But at the end of the day, the application for F1 resides primarily on the CPU, and then we're accelerating computation down in the FPGA. When we think about pipelining and parallelism at a hardware level in an FPGA, it's important to characterize this type of parallelism, pipelining, as being somewhat different from what happens in traditional CPU programming and GPUs as well. In the case of hardware accelerated computing, the more that you can take advantage of pipelining, the higher performance and application you can think of. Pipelining is very similar, or data flow programming is very similar to what happens in the real world in many, many sectors. So think of an assembly line or a complex logistics problem such as we see on the right here, where you have many, many parallel tasks, and those tasks can be reconfigured over time as needed, adding and subtracting perhaps workers, and then data in the form of, in this case, either cars moving down the assembly line or perhaps packages moving down through the logistics channel are then processed through this stream of connected pipelined processes, whether they're people, machines, or constrained resources of various sorts. In an FPGA, you can easily implement these types of pipelines using a streaming programming model, using processes and data that are related in a way that might be subtly different than what you do in a CPU application. And the programming models and methods that are used for FPGAs often are oriented around this type of processing. So to summarize, an FPGA is very different from a CPU, very different from a GPU in that it has a very granular architecture. There's no instruction set unless you create one yourself, and that allows you to create a wide variety of accelerated applications, but it does require a certain amount of hardware skill and hardware understanding. But if you can do this, if you can create the bit widths that are the most appropriate for your application, take advantage of parallelism and pipelining, you can accelerate many applications, and I'll describe some of those in a few moments, quite dramatically using FPGAs. Well, let's dive a little bit deeper now into the F1 instances themselves. We'll talk about what's inside of an F1 instance, how the FPGAs are interconnected, and then we'll later get into how we actually program these using the development tools that are provided with the F1. When we launched, or when we announced the FPGA instances, the F1 instances, we had a number of goals in mind. And some of these goals are very, very important and go beyond simply providing FPGA capabilities in the cloud. One of our most important goals was to make acceleration capabilities, FPGAs in particular, available to a vastly larger community of developers, right? So historically, FPGAs, which have been around for quite some time, by the way, FPGAs have been used for specialized appliances, they've been used for embedded systems, but they haven't really been available to the general community of programmers and researchers in the way that would enable a wider range of applications to be developed. The second thing that we had in mind was to create a large amount of FPGA logic dedicated to a particular customer or application. We don't want to start small here. We want to start with large FPGAs and multiple FPGAs in the largest F1, allowing a wider variety of applications to be developed in this new instance type. Another important goal here was to vastly simplify the development process, and we'll talk about how we do that in a few moments, but one of the most important aspects to that is abstracting the I/O. FPGA developers historically have faced two challenges. One challenge is developing the actual logic, the pipelined architectures, the parallel architectures, perhaps refactoring a traditional software application for use in the FPGA. But then the other challenge is the I/O, figuring out how to get data to and from the FPGA in an efficient manner. And we're really helping to simplify that through the use of an FPGA shell that I'll describe later. Another thing that we want to do is allow application developers and end customers to get access to an ecosystem of tools. Now today there's a variety of tools available from Xilinx, for example, and from third-party partners. We do anticipate that over time FPGA development tools will be provided in our marketplace, will be widely available because they now have a platform that's easy to target in the cloud. And then on the application side, it's very important that we provide application developers using FPGAs to get access to customers. And there are many, many customers today that choose and deploy applications using the AWS marketplace. The ability to offer FPGA accelerated applications in the marketplace will be very, very impactful for furthering the use of FPGA acceleration in the broader market. Well, let's dive a little bit deeper now into the F1 instance and what it consists of. There's actually two sizes of the F1. We're providing the F1 2X large, which has a single VU9P Xilinx FPGA, and then the F1 16X large, which delivers 8 FPGAs in a single instance. Each of those FPGAs has associated with it 4 DDR4 interfaces, 4 memory controllers, giving you access from each of these FPGAs to 64 gigabytes of ECC protected memory. And that's important because many FPGA applications require access, very high rate access to memory in order to keep the pipelines busy, to keep the applications fed. Local memory is very, very important for most FPGA applications. Another important aspect of the UltraScale plus FPGAs that we've chosen, these are 16 nanometer devices, the most modern Xilinx UltraScale devices, is that they provide a large number of logic elements, right, programmable logic cells in the FPGAs. Each of the FPGAs provides over 2 million accessible FPGA programmable logic cells. In addition, if you're familiar with FPGAs, they also provide programmable DSP blocks or math blocks that can be used to implement higher level math functions. And there's over 5,000 of these DSP blocks available to programmers in each one of these FPGAs in the F1. Another important aspect of F1 is interconnect. So in the largest size, the F1 16X large, we are providing 2 forms of interconnect from FPGA to FPGA. The first of these we're calling FPGA link, and this is a bidirectional ring interface that allows you to create streaming applications that rapidly move data from one FPGA to another without going up through the host or across a bus architecture. This is a very flexible bidirectional ring, perfect for doing things like streaming video data or other types of data from one processing element to another in the FPGAs and across FPGAs. The second type of interconnect is very similar to what we're providing with our P2 GPU instances, and that's dedicated PCI Express interconnectivity we call FPGA Direct. And this is dedicated PCI Express lanes. You have full bandwidth from one FPGA to another. Any FPGA in that 16X large can communicate with another via this PCI Express interface. So 2 interfaces provided between FPGAs. One is the fully connected PCI Express interface, and the other one is this bidirectional ring interface provided with FPGA link. Now on the server side, the host server in the F1 16X large is also quite powerful. So focusing on the 16X large size for a moment, notice that there are 64 vCPUs provided in this instance type. It's one of our most powerful instance types in EC2 today. And then, of course, with the addition of the FPGAs, from a raw performance perspective, extremely powerful platform. We also provide nearly a terabyte of RAM in the 16X large on the server side and NVMe-based instance storage. Notice also that the network bandwidth is higher than any previously announced EC2 instance, 30 gig performance from instance to instance in a placement group on EC2. And this allows you to cluster multiple F1 instances with high-performance networking, get access to high-performance CPUs on the server side, lots of RAM, in addition to the 8 very powerful FPGAs provided in each instance. Let's dive a little bit deeper into the FPGA. And this may be familiar to those of you who are already using FPGAs and understand the architecture. But for those who are not, it's important to understand that the FPGAs, the Xilinx UltraScale FPGAs, provide a variety of resources that are available to developers. From an application perspective, from an algorithm perspective, the 2 most important elements of these are the system logic blocks and these DSP blocks that I mentioned before. System logic blocks are logical elements that can be programmed either through automated tools or through more manual methods to create logic circuits of an arbitrary width, of an arbitrary type. Each of these logic elements has some control functions, it has registers, it has memory, and can be used to create simple decode functions, state machines, and other such low-level applications. They can also be connected together to create much more complicated code, mathematical code, for example, or mathematical circuits. Because math is so important to many of the applications that are deployed in FPGAs, math such as single and double precision floating point, or arbitrary precision or fixed precision math, the DSP blocks available in FPGAs can be used to efficiently create larger numbers of operators, such as dividers, multipliers, multiply accumulates. And the system logic blocks being used for control logic and integer types of operations combined with the DSP blocks allows you to create either automatically with synthesis and place and route tools or in a more manual process using hardware description languages to create very complex algorithmic types of applications in the FPGA and to arrange those in a highly parallel pipelined manner. Now, the other two elements mentioned on here, the I/O blocks and the block RAM, are also very, very important. Now, the I/O blocks are configurable logic elements that are arranged around the outside of an FPGA that allow you to create a variety of different interfaces. For example, a memory interface that connects to your DDR4 or a PCI Express interface or just general purpose pinouts. Now, in the F1 instance, we really abstract most of that I/O. I'll talk about the FPGA shell in a moment so that you really have to think very little about the I/O blocks. You'll just access the I/O that's available to you in this shell using standardized bus interfaces. Another important aspect of FPGAs is they do have quite a lot of onboard memory, either distributed in the logic cells themselves or in some dedicated RAM that we've summarized here as block RAM. But there's really multiple layers and types of RAM that are available directly inside the FPGA. And this is important because, as I mentioned, applications and algorithms that are accelerated in hardware using FPGAs are often very memory intensive. They require a very wide, fast access to different tiers, if you will, of memory. Distributed RAM, block RAM, external DDR4, very wide access and fast access to keep the pipelines busy, to keep the applications running efficiently. I mentioned before this FPGA shell. This shell is very important because, as I said, one of the most difficult aspects of developing FPGA-based applications historically has been in creating the right I/O. Figuring out, for example, how to DMA data from a host into the FPGA, getting the most efficient use of streaming, for example, accessing memory. We can make this a lot easier by abstracting much of these details using this FPGA shell. It's a pre-configured, pre-tested, and it's secure way of dealing with I/O in the FPGA. This allows application developers to focus just on their core algorithms, on their accelerated needs, and not focus so much of their energy on how they get the data in and out of the FPGA. The FPGA shell makes extensive use of the AXI interface, which is a bus interface, internal FPGA bus interface supported by Xilinx, and it makes a very effective way to connect your logic into the shell and hence out to the other peripherals or up to the server. I'd like to talk for a few minutes now about the AFI, the Amazon FPGA image. If you're familiar with using EC2 today, the Amazon machine image, or AMI, is a very important concept. The AMI allows an application developer or an IT administrator, for example, to create a golden image, to create a template, a prototype of a virtual machine that can be quickly loaded into an EC2 instance. For example, an AMI would have the operating system, it would have your applications on it, it would be pre-configured and ready to go and ready to launch onto an EC2 instance. Now, in the case of the F1 instance, we also have a bit stream. We have data that we need to download into the FPGA in order to configure that FPGA in support of the particular application that we're deploying. So we need the equivalent to the AMI running in that FPGA, and we call that an AFI, the Amazon FPGA image. And now, just like the AMIs, it's often very, very important that software developers or IT administrators are confident that the logic that is going to be in that FPGA is secure. And so a very important aspect of our AFI support tools, of the way that we manage these bit streams for the FPGA, is security. Now, you can associate multiple AFIs with a single EC2 F1 instance and its AMI. In fact, you could load different AFIs in a second or less down into the FPGA to swap them in and out. But in all cases, this will be a very secure, encrypted environment. The bit stream that you download to the AFI, for example, if you're delivering an application to an end customer, is going to be secure. It can't be copied or viewed. It can't be edited. We take care of that security, whether you're launching this as a complete software as a service, for example, where your customers may not even know there's an FPGA, or deploying it to somebody who may be very FPGA savvy. They have no access to the underlying FPGA code. So to summarize, the AMI, the Amazon Machine Image, is used to boot and load that EC2 F1 instance just as you boot and load any other EC2 instance today. Once loaded, the EC2 F1 instance running your application can then invoke and load various AFIs, Amazon FPGA images, to implement different applications over time, or perhaps swap in and out different functions that are needed by an application over the course of its run. I'd like to switch now and talk about some of the use cases for FPGAs. FPGAs are not new. They've actually been around for quite some years, and there's been many successes in high-performance computing using FPGAs to accelerate highly parallel applications. And one example of that is in genomics. In fact, FPGA acceleration of genomics has been around for some time. Edico Genome is a great example of a company that is providing hardware-accelerated appliances that can be installed on-premise into a customer's data center to dramatically accelerate genomics processing. Now, a lot of genomics processing today is actually running in the cloud on AWS. It just makes sense. There's availability of vast amounts of storage space. It's very cost-effective, access to large amounts of CPUs in the cloud. But historically, FPGAs have not been available on the cloud. And so an organization like Edico Genome that's very, very good at accelerating applications using FPGAs in this space has not had access to the customers that are increasingly deploying in the cloud using AWS. So Edico Genome, of course, is one of our partners in the F1, quickly migrating their applications into the F1 instance so that they can provide FPGA-accelerated genomics processing pipelines to genomics customers that are running today on AWS. It's a great example of parallelism being used to accelerate a complex pipeline. In the case of genomics, by using hardware acceleration, it is quite possible to get a whole genome analysis down from many, many hours down to just minutes, greatly changing the way that genomics can be used for translational medicine, for fast results, and improve healthcare. Another example of FPGA computing is in the financial sector. Now, the financial sector has also deployed FPGAs for quite some years for a variety of use cases. The most common use case in the financial sector for FPGAs would be in areas like high-frequency trading, embedded systems that would automatically generate trades based on very low latency feed information coming from exchanges. But there's actually other use cases for FPGAs in the financial sector. High-performance simulations, for example, Monte Carlo simulations, risk simulations, can be greatly accelerated through the use of the massive levels of parallelism that are available in FPGAs. And Maxillr is one of the organizations that's been in this space for some years now, providing high-level programming tools and appliances that can be used to accelerate a variety of different risk and options valuations types of products. Maxillr is a partner with F1, migrating their software stacks and their hardware acceleration capabilities to the F1 instance in support of the financial sector customers that are running already on AWS. Here's another excellent example. Video processing is another use case in which FPGAs have been used for quite some time. Streaming applications, video transcoding, getting different video streams fused together into one, or perhaps doing things like object detection or enhancement and so forth. These are applications that are well known to be very, very good in FPGAs. And in fact, there are quite a few products available in the market today in the video processing space that are actually FPGA based. Now, because so many workloads in the video content delivery area have been moving to the cloud, it's important that we have hardware acceleration available for these types of applications. Now, what was particularly exciting about NG Codec is that they were able to demonstrate live at our reInvent conference when we announced the F1 instance a transcoding demo, H.264 to H.265 transcoding demonstration running live at reInvent after only 3 weeks of having access to the new F1 FPGA instance. And that really did help us to understand the importance of capabilities like the FPGA shell to abstract that I/O so that a partner such as NG Codec could really focus on the core application and that migration. And there will be many, many other use cases in video processing that will appear over time on the F1 FPGA instances. And lastly, I'd like to talk about accelerated analytics. And there are so many new and interesting use cases for this. Rift, for example, is an organization, a company that provides hardware accelerated appliances for data discovery, for text mining, for search types of applications. And Rift is also currently porting their applications to the F1 instance in support of these applications for our customers that are looking for much higher performance data analytics and data search capabilities. And these are just a few examples. There are many, many other examples of how FPGAs can be used to accelerate all kinds of applications across industries. And many of these applications, of course, will be offered in the near future on the AWS marketplace to our many, many customers that are seeking increasingly higher performance solutions. Well, let's switch now and let's talk about the development process and how you as an application developer, perhaps somebody who's familiar with FPGA programming or maybe who's new to FPGA programming, can develop an application and deploy it and perhaps offer that on the AWS marketplace. Now, we've summarized the development steps for FPGA into just 4 steps here. There's a lot of complexity, of course, involved with programming for FPGAs. There's some new skills to be learned if you haven't done hardware development in the past or haven't done FPGA design in the past. There are certainly some new skills, but it is achievable by most application developers, including software developers, once you begin to understand concepts like parallelism and pipelining and the somewhat longer development cycle of using an FPGA through the place and route process. But we can summarize it as follows. So the first step is to get access to the development tools themselves. Now, historically, that has meant licensing, downloading very large amounts of software from an FPGA vendor, in this case Xilinx, installing those on your local machine, installing different libraries, and beginning to use simulation tools and place and route tools to develop the bit stream. Now, in combination with developing that bit stream, you needed to have hardware available to you, so you would typically buy a reference design, a reference kit, some trading hardware, for example, a board that might be PCI Express attached, or it might be a separate type of board that sits on your desk. What's dramatically simpler, of course, on AWS is that we can provide these developer tools as a pre-configured, ready-to-go AMI, Amazon Machine Image, that you would run on a standard EC2 instance, such as one of our C4 instances. So now you have a complete, tested and pre-configured development environment for FPGAs ready to use in the cloud in a matter of minutes. Nothing to download, nothing to configure, nothing to license. So that environment is what you'll use initially to develop the FPGA code, get it ready for downloading to the F1 instance. Now the software that you'll use is Xilinx Vivado, or in the future the SDXL software, which is a higher level programming environment from Xilinx. And this will allow you to code using traditional FPGA languages like VHDL and Verilog, or perhaps move into higher level methods of programming using OpenCL, for example. OpenCL I'll talk about a little bit later, but OpenCL allows you to express your logic in a more C-like environment and also helps you to abstract the I/O to and from the application running on the server side. Now, in combination with those Xilinx tools, the Vivado or SDXL software, we also provide an HDK, a hardware development kit. And that involves the FPGA shell that I described before. So it provides the abstractions, the libraries that are needed to express the I/O in and out of that FPGA. So the FPGA developer AMI, in combination with a hardware development kit, allows you to move forward with your development, to simulate, to generate bit streams, to do place and route, and get ready for that downloading. Now, steps 1 and 2, you don't really need to have access to the F1 instance. You can do most of this work using a standard EC2 instance like a C4 or an M4 in order to generate that logic, simulate that logic, and get it ready for use. Now, step 3, after you've successfully simulated the design, you begin to run synthesis and place and route. And this is where you invoke these computationally intensive processes in the Xilinx tools to actually take the logic, think of it as the compiled logic for your application, and then iteratively place and route that through automation into the FPGA. Now that could be a fairly lengthy process. It could actually take hours, and so you really do want to focus a lot of your effort on simulation. Make sure that your application is functionally correct using simulation tools before you begin that place and route process and synthesis process. The result of the synthesis process and the place and route process is what's called a design checkpoint, a DCP. And that is a compiled and synthesized and placed logic that can now be generated as an Amazon FPGA image, an AFI, using tools that we provide. Now, a very important aspect of this, before you get that DCP down into the AFI ready for customers, you're going to submit it to our tools. We will encrypt it. We will protect it. And so the AFI that your customers will consume or that will be deployed into an EC2 instance on behalf of your applications, for example, is secure, cannot be examined by others. It's a very secure way for you to deploy your applications into the FPGA. So in that's step 4, right? So your F1 instance will now launch. You load that AFI, which includes your DCP, your design checkpoint, and our FPGA shell, into the FPGA. We manage that for you, make sure it's secure and protected, has a unique ID, and then you can present that application to your customers. So to summarize those steps, you'll use the front-end design tools provided in Xilinx Vivado, and these include digital simulation tools. They include language compilers and so forth at the front end. You'll run those tools on one of our standard EC2 instances, C4 or M4, for example. You then, in those same tools, you begin the place and route process, and you only do that after you're reasonably comfortable that in simulation you've got the design correct, because the place and route process can take some time. That place and route process generates a DCP file that is then ingested into our tools to create an encrypted AFI, Amazon FPGA image. That AFI can then be loaded into the FPGA in the F1 instance. And in fact, you could load different AFIs over time in response to the needs of a particular application. That Amazon machine image that we provide for the FPGA development environment is provided in the marketplace. There's no charge for this. Here, for example, you can see that we are selecting from the AMIs that are available in the Amazon marketplace, the development environment, for example, using CentOS operating system, selecting a version of Vivado, ready for launching into an instance, for example, a C4. And we certainly anticipate that over time there'll be a wide variety of tools available from Xilinx, from ourselves, and from third parties in support of development of F1 applications. When you launch that AMI on your selected instance type, it'll come up, it'll configure itself, it'll be ready to use either in batch mode or in interactive mode, again, using the standard user interface provided by Xilinx. So if you're familiar with developing using the Xilinx Vivado tools, then this will be very familiar to you when working in the cloud. But the benefit, of course, is you don't have to download Vivado, you don't have to run it on a local machine, you don't have to worry about versioning of it. We make sure that the versions that are available are the right versions and equipped with the right libraries in support of the FPGA shell to allow F1 development to be done much more efficiently. So Xilinx Vivado using VHDL or Verilog or soon SDXL, sorry for the typo there, will allow you to operate at a higher level of abstraction if you like. Use the scripts that we provide to create that FPGA logic, synthesize it and place it around, route it, and create that DCP, that design checkpoint. Design checkpoint is a relatively new concept for Xilinx FPGAs. It's basically the bit stream, and it is used to do partial reconfiguration in the FPGA for the logic that you're interested in, so that we handle the FPGA shell as a separate part of the application. We keep those things separated, so that allows us to have a more efficient and faster place and route, and also make sure that your application, and our applications in the shell don't conflict with each other. So that last step I mentioned, you want to get that AFI generated from your DCP. That is an encrypted and AFI that has a unique ID. You use that unique ID to download the AFI onto the FPGAs that are in your F1 instances. Either one or multiple F1s might have the same AFI. And conversely, maybe a single F1 instance over time can swap in and out different AFIs. So maybe, for some number of hours or minutes or seconds, you need one AFI loaded in the application, but then due to changing application needs, or maybe because you just need to extend it to different types of functions, you might swap in a different AFI to do some different operations in the FPGAs, and that's certainly supported using the AFI management tools. They're all API driven, very easy to use from the software side using APIs. Well, let's talk for a moment about delivering FPGA applications to end customers on the marketplace. I mentioned some examples before of partners that are quickly moving into the AWS marketplace with their solutions, and there will be many, many more. And there are certainly opportunities here for application developers who have FPGA expertise to now build new and innovative products and offer them to literally millions of customers who are either running accounts on AWS or are end users of applications that are deployed on AWS today. So it's a huge potential marketplace for developers of FPGA-based systems. I summarized this before, but I'll summarize it again. The Amazon machine image is today what is used to deliver software through the marketplace. So for example, if you have an innovative database related solution or security solution, maybe some development tools, you would offer those today through the AWS marketplace by creating an Amazon machine image that's uniquely yours and tagged, and can be offered to end customers using a variety of licensing methods through the AWS marketplace. You could charge hourly, you could charge monthly. There's a number of different monetization methods available through the marketplace. With the FPGA instances, you now have the ability to associate with an AMI an AFI, your Amazon FPGA image. And just like the AMI, it's given a unique tag. It's yours. We can track it. It's secure. Your end users cannot copy it. And that can be delivered through the marketplace to a much larger number of customers than would otherwise be practical using physical implementations, right? Delivering appliances to your customers with FPGAs is a much more difficult proposition than actually delivering via the cloud. So it vastly simplifies the delivery of FPGA-based applications to end customers. And just to summarize the benefits of this for application developers, as I said, this makes it far easier for a developer of an FPGA accelerated solution, whether it's a startup or an existing developer of FPGA-based appliances, to offer those solutions using a combination of an AMI and an AFI, and offer those in a very secure manner to your end customers. And those end customers might be very large enterprises, they might be other startups, they might be any number of different types of customers. We have well over 1 million customers today on AWS who have access to the marketplace and can purchase products and services via that marketplace. So it's a very large market that's now available to FPGA experts. Of course, you can discover new customers that you hadn't even considered before. As I said, there are so many customers today that are deployed on AWS and that are accessing software via the marketplace. You now have access to a sales channel that is much, much easier. The monetization is very easy. We take care of the transactions, remit to the vendors of the software solutions. It's just a far easier way to deploy your applications, FPGA-based applications, to customers. And of course, we take care of billing and payments and tracking of this, not just in the US, but around the world. And as I said before, it is secure. So we encrypt your bit stream, your DCPs in the AFI. We give them unique tags. We can track them. They cannot be copied by your customers or by your competitors and other partners that may be in the cloud as well. They are uniquely yours and protected from use or copying from others. And the marketplace also provides an easier method of product support. It makes it easy for someone who's deployed via the marketplace to communicate with you about issues they may have with your software or feedback on your solution. The AWS Marketplace provides a very robust set of communication services, in particular the product support connection, that makes it much easier to set up and manage customer support in support of your end customers running FPGA applications. So I'd like to close with some glossary terms. If you're new to FPGAs, some of these things that I've talked about very quickly are new, and so it's helpful to go through this. If you're an existing FPGA user, it's helpful to know how things like the AFI and the DCPs and so forth relate, and also to understand how we might extend this in the future. And we're absolutely interested in your feedback today. We've asked some questions at the beginning of the session, but please feel free to ask questions in the chat window or to return with us later with feedback on what we're offering. But I'll walk through some of these glossary items. FPGAs, of course, if you're familiar with them, the field programmable gate array, these have been around for quite some time. Xilinx began offering these, for example, back in 1985, so they have a long history. The AFI, the Amazon FPGA image, allows you to encapsulate the logic that will be programmed into an FPGA device into a secure format in which your bit stream, your DCP, as I mentioned before, can be loaded in alongside of our shell and programmed into that FPGA in the F1 very efficiently in a very secure manner. Hardware description language. If you're familiar with software programming in languages like C, for example, or Java, hardware description languages are analogous to those, but there are lower level languages that allow you to express digital logic. Now, historically, HDLs have included VHDL and Verilog. Increasingly, higher level tools such as OpenCL have been made available to make hardware development somewhat easier. You do still need to understand digital logic concepts, pipelining, parallelism, and so forth to make good, efficient use of HDLs, but these are skills that are actually not difficult to learn by most software engineers. Vivado, SDXL, these are design tools provided by Xilinx that allow you to program the FPGAs. They include simulation tools, they include place and route tools that can be used to map your HDL or higher level logic down into that FPGA in combination with the hardware, the HDK, the hardware development kit that we provide. And it's important to know that Vivado and SDXL were provided at no charge by AWS. You can get access to these for use with the F1 in the cloud. It makes it very easy to get started. I mentioned before OpenCL. This is an emerging and evolving environment or higher level language that provides both the ability to express in a C-like language the actual logic of your application and compile that down into hardware, as well as to help you to abstract some of the I/O, in particular on the software side, on the CPU side. And OpenCL is also intended to be portable. So there are OpenCL compilers that will target GPUs, as well as the ability to target FPGAs. I mentioned the HDK. This is a set of tools, more importantly, a set of libraries and documentation that help you to work with the I/O that we have abstracted in the FPGA shell. And that's provided with the development environment, the AMI that we provide. I mentioned AXI in passing. AXI is an important part of that HDK. AXI is a bus format internally to the FPGA, and we use AXI extensively to abstract the I/O. For example, to allow you to connect to PCI Express and up to the host. Those are provided as AXI interfaces. And the developer AMI I mentioned before. This is available in the marketplace, can run on a variety of instance types, and that includes the tools I mentioned before, Xilinx Vivado, for example, to allow you to simulate, synthesize, and place and route your FPGA logic and to create that AFI, that Amazon FPGA image. And finally, these terms I mentioned in passing, if you're not familiar with FPGAs, synthesis is a very important process. That takes the lower level hardware description language that you've written or the higher level OpenCL, actually synthesizes that down into low level logic gates and registers and other architectures for the FPGA. It's a very important part of the process, and it can be quite compute intensive. Synthesis can take quite some time to run. So it's important that before you run synthesis and place and route that you get make use of simulation so you don't have to run synthesis, place and route too often. Place and route, of course, follows synthesis. That's where you actually take the synthesized logic and you place it into the FPGA, you interconnect it, and create the actual bit stream that will be generated for the FPGA. In our case, in the form of an AFI via a design checkpoint, DCP. So the DCP encapsulates the bit stream. The DCP is combined with other logic that we provide in the FPGA shell to create the AFI. So that was a lot of information. We're super excited about the F1 FPGA instances. There are many more details that you can find on the F1 landing page, and I've included a link here. This will include, as we announce new capabilities, and the preview that we're in today moves into general availability, what other capabilities and the development tools will be available. So if you're interested in getting access to the F1 during the preview process, please visit that page and sign up for the F1 preview. We have a lot of interest in the F1. Lots of customers are signing up for that preview program with lots of different interesting use cases. So we're super excited about what types of applications will be developed in the near future. We're also excited about the potential for many of these applications to land on the AWS Marketplace. If you're interested in that program, how it looks, how you can monetize software and secure it, please visit the Marketplace landing page. If you're in the public sector, in the educational sector, we have a number of programs, credit programs, assistance for educators as well as students to get started. And certainly FPGA education is an important part of that, and that is in the AWS Educate program. I've also included links to the 4 partners that I mentioned, and there are certainly more that will be mentioned in the F1 partner page when you visit there. So with that, I'd like to step back. We've got about 5 minutes and solicit any questions that you might have in the chat window. I have with me Chris Petty, Nafa Bishara, and Gadi Hood, who can chime in as needed to answer some of these questions. Well, we've got lots of questions that have come in, and I'm just going to grab a few of these that I think are quite relevant. So the one question is it required to do the development of your design using the cloud, using C4 and M4 instance, for example, as opposed to doing it on the local machine. Of course, many FPGA designers already have FPGA development tools installed on their systems. Absolutely, you can download that hardware development kit and do it on your own machine. But you know, it will be much more efficient and cost effective if you don't have the Vivado tools to do that on the cloud. And yeah, questions about chip scope. I didn't cover chip scope in the presentation, but I want to cover that briefly right now. So chip scope is a hardware level debugging environment provided by Xilinx, in the Vivado tools. Chip scope normally requires direct hardware access to the FPGA on the development board that you're using. In the cloud, we are providing chip scope capabilities. We have the ability to connect to the FPGA remotely using chip scope in the tools. And so when you're running on F1, you want to do that in-system debugging, you can use chip scope to do that. Here's an excellent question related to security that Chris Petty has just answered in the chat window. Will the FPGA image and state be scrubbed when I return the F1 instance? And that's a very important concept. Security is very, very important to AWS and our customers. Absolutely, your FPGA logic will be completely scrubbed, wiped from the FPGA in between uses by other customers and applications. All right, another question. So another question, will model sim simulation software be available? Now this is a great question because there's actually a wide variety of different FPGA-based tools that are available out there today. You can certainly deploy and run those tools today on AWS, you know, in accordance with, of course, the ISV license agreements. So if you're running a third-party simulator from a major EDA vendor, or perhaps running some other FPGA-related software, simply verify with your ISV that you have the ability to run those licenses in the cloud. You can certainly deploy them. We do anticipate that you know, after or soon after the launch of the F1 instance, there will appear a wide variety of different FPGA-based application environment simulators and the like in the AWS marketplace as well. And then lastly, if I already have a Xilinx license, can I do my development? So this is related to whether you can develop on-premise. And if you have a license to Vivado, for example, and SDXL that you're running on-premise, you can certainly continue to use those. We are providing the tools at no charge on the cloud, so if you prefer to do FPGA development in the cloud using one of our instances, C4 or M4, for example, that can be done at no charge. Of course, you'll have a charge for the underlying instance that you're running on the cloud, but most customers will find that very cost-effective for doing their FPGA development. Great. Well, thank you very much for all these questions. And again, please don't hesitate to reach out to us. We've got more information that we can provide. Keep an eye on the F1 page, on the EC2 instance page. There'll be much more information being provided as we get closer to general availability. Thank you all very much. We really enjoyed the session today. Looking forward to seeing many, many new types of interesting applications being developed and offered via the AWS Marketplace on AWS.
Awesome. Thanks a lot, David, for a great presentation. I'd like to thank the moderators for answering the audience questions. We do apologize we did not have a chance to get to all of them, but we will be saving the Q&A log for review after the fact. So if you have any comments on our previous and upcoming webinars or suggestions on the topics you wish AWS will cover in future webinars, please drop us a line at aws-webcast@amazon.com. Your feedback will help us to improve our webinar programming. Thank you to the audience for taking the time to join us today, and enjoy the rest of your day.